So we already know how to work with two orthogonal vanishing points. Now there is another problem. We know how to draw rectangles. But there is a problem about selecting a third vanishing point for this rectangle. For example, we could draw third vanishing point like this, and then connect to other vanishing points. We could draw it like this, for example, and on the first side, you can't really tell which of these ways to draw the box is correct and which is not correct. Or you can feel that some of these boxes are kind of wonky, distorted, or something like this, but you can't really argue about correctness without additional constructions. So, but if you think about the geometry and imagine there is some plane, and you select at this plane the base for our rectangle. So there are two orthogonal lines, which would later form a foundation for our rectangle. And we know that in dimension 3, you can select the third orthogonal line in a unique way. There is only one line which should be orthogonal to these two lines. So, among all these ways to draw a rectangle, a box, there should be some way which is more correct than other ways, at least if you add some additional information. How do we draw? And the question becomes the following. How do we draw vanishing points for this kind of set of lines, which forms, as we say in mathematics, an orthogonal basis, if you consider this point as a region of vector space? To do it, we again draw a picture plane and a viewer. But this time we will draw it a bit differently. We will start a drawing from the other direction. So this is the picture plane. A bit wonky, but it's okay. I want it to be rotated like this, because in the general position we want it to be not parallel to any of these lines. Otherwise it will be some edge case which should be handled separately. And now we select some point as a viewer position, and we draw these lines. We parallel shift them toward viewer position. So we have this line. Let's show them with the color. This is this line. Let's draw it more precisely. So we have something like this. There we have a vanishing point, so let's denote it as A, B, and C. This is a vanishing point for A. Then we have bottom direction, vertical direction, green line, parallel shifted to the viewer point, viewer position, obtain vanishing point C, and finally we could use this line to obtain the third vanishing point. Like this. So this is vanishing point B. Now, if we connect all vanishing points, we will get a rectangle. We will get some triangle. It's a very common idea that you can just draw some triangle and use it as vanishing points in so-called 3 points perspective. Well, this idea is wrong. You can just do it however you want, because there is a viewing position. And we can project our viewing position to this triangle, and it will be defined. So if we have viewing position and directions, we can draw vanishing points. Vanishing points will be defined in a unique way, but the opposite is true as well. If you have some set of vanishing points, like we have a page, then if you draw some triangle, there, in some cases, and for some triangles, you could draw a viewing direction. But where do we place this viewing direction? Here, or maybe we place it here, or here, or here, or here. It is just impossible to say without additional knowledge. And we can see that the core of this knowledge could be explored when we think about figures like this simplex. So there is some corner. It's if we draw it like this, so we have a foundation of our pyramid, and we have our viewing position. Let's place it there. And there. And then we will have some kind of a pyramid, which foundation is vanishing points A, vanishing point B, and vanishing point C. And we know that all these angles are 90 degrees, because all these vanishing points are orthogonal. And as we already explored how viewer position and orthogonal vanishing points are related. They have a right angle here. So we have 3 right angles. There will be another right angle, and there is invisible right angle in this direction. So if you want to make this picture a bit more clear, we could draw it like this. So there is our basis, orthogonal basis, again, and we just draw triangle like this. So this is our picture plane, this triangle. This is vanishing point A, vanishing point B, vanishing point C. And all these angles are right angles. They are equal to 90 degrees. And then to find out the relationship between viewing direction and all this construction, you have to recall the following fact. If you have some segment, then you can consider all points from which you can look at this segment at right angle. So you can look at it from here, from the right angle, from there, and so on. And all these points, if you think about a plane, all these points form a circle. Circles in perspective are very hard to draw, especially freehand, so it is a bit messy. But essentially you have a full circle. You select any point at this circle, and the corresponding angle will be equal to 90 degrees. Then you can rotate this thing. You can select any kind of plane and do the same thing. You will have again another circle. And if you consider all rotations at the same time, you will obtain that it is an entire sphere. We say that geometrically, if you place a restriction that you should look at this segment at 90-degree angle, it should be visible in this angle. Then you have a description for all points which satisfy this restriction. It is a sphere which center is at the center of this segment and which radius is half of this segment. So, and we have there very similar situation. We have there some straight angle, and we know that this thing should lie on some sphere. Essentially, we want to find a projection here. We will find this projection in a bit roundabout way. So we have there a sphere like this. Let's draw a sphere. Let's draw a segment of this sphere, a half circle. And we know that there are half circles for all of these segments. Let's consider a pair of these spheres. For example, this sphere, this half sphere. Let's paint it with some solid color. And this half circle, this is the continuation of the half circle. And this is a visible part of another half circle, which passes through. And we can see that there is an intersection, which we want to not find, but we want to describe it in a bit different way. Especially we are interested in the projection of this point. Well, it is one of these points. But if we will draw the entire sphere for all of these things, let's just sketch the sphere in a very sketchy way. And we could sketch the sphere for this part. We will see that this black point at the top of the pyramid, this black point lies on the intersection. So we have some sphere. For example, this is sphere 1, this is sphere 2, and it lies on the intersection. This point viewer position belongs to the intersection of sphere 1 and sphere 2. But when we have two spheres and we intersect them with each other, we have a full circle. Let's draw it like this. So their intersection is a circle. which is centered at this line which connects both of the spheres. So we have these sections for these spheres. And we have there an intersection in red. And somewhere on this half sphere, we will have our point. But the interesting part is not really this half sphere. The interesting part is projection of this half sphere, of this half circle, on our plane, this one. We see that this line, which is the projection of this circle, is orthogonal to the line which connects centers of these circles. So, if we have some triangle, again, as a base for our vanishing points, and we consider the center of the sphere 1, the center of the sphere 2, and we connect these points, we know that this point should be projected somewhere on the orthogonal to this thing. But so we have this thing, and our projection should lie somewhere on the orthogonal to it. In fact, it would be this orthogonal, which goes from the point. Why? Because we know that we should lie on intersection of spheres. And if we consider the intersection of spheres, it will look like this. It will pass through this vertex of our triangle, and it will go through orthogonally to this line. So let's just draw it a bit more precisely. We have this half circle. There is the top point. There are our spheres, which we were drawing before. I'm drawing this picture just to make it clear that we are actually in the situation of this thing, of this diagram. So you have there a section of the sphere. We have there some section of a smaller sphere. And we know that our point, original point, which is the view position, should be somewhere on this thing. So it should be projected on this, let's show it in yellow, this yellow line. Notice that these lines are orthogonal, but if you think about it, this small triangle is similar to the outer triangle. It is just the outer triangle which was reduced twice, with the center of the scale being this point. But if these two lines are parallel, then if we continue this line, it would be orthogonal to it. So this line is the height of our triangle. So our point which we want to find will lie on intersection of heights of our triangle. Let's draw just a triangle. We draw all heights. From geometry, we know that all heights of the triangle should intersect in the same point. And as we showed it, our viewing direction, our projection of viewer position on the picture plane should lie on the green line, it should lie on this magenta line, and it should lie on this dark blue line. So it should lie in the intersection of all of these lines. But there is only one point which is an intersection of these three lines. So we found out how to describe the projection. And we can resolve this question. If we have a page and we drew some points, vanishing points for our picture, let's draw them like this to be more generic. So we can find the viewing direction by intersecting all the heights of our triangle. Of course, it will never be precise, because when you are drawing, when you are sketching, you are not doing precise drafts, you are just doing an estimation, and of course when you are doing an estimation there is a margin of error that will manifest itself in some way. So this will be a viewing direction, and this will be a complete, now this is a complete variant of so-called 3-point perspective. But now there is a question. So we usually don't want to draw some triangle and then hope that our viewing direction will be where we want it to be. We want to start from the viewing direction, because, for example, if we had some weird triangle and our viewing direction is there, well, then the whole drawing is ruined. We are looking at the corner of our page. So it means that areas outside of some circle, outside of some area, they will be a bit more distorted than area there. So a large part of your page will be looking, well, not really good. To avoid it, we usually start with the viewing direction. So we have there our viewing direction. We have some vanishing point 1. Then we already know how to find an orthogonal vanishing point. We can just draw some horizon line. This is a part where we still have some degree of freedom. We again find a station point which works for this horizon line. Let's draw it with the blue line. This is the station point for horizon line 1, or horizon line, let's say that it is a horizon line 3, just to be pretty. So this will be vanishing point 2, which is orthogonal to the vanishing point 1. And now we don't really have any degree of freedom. we know that our third vanishing point should be somewhere on this line. Let's draw it as a green. Somewhere on this line we have our third vanishing point. How do we find this vanishing point? Well, we also know that it should be at intersection of all heights of our triangle, like there. It means that when we are drawing, if we think that this is our viewing direction, then we can connect it with all vanishing points. And we know that these lines, these segments should be a height to side which goes somewhere there, but then we can find this side by just drawing an orthogonal line to this future height of the triangle. So we draw it like this. This will be a right angle. Continue, and we finally found our vanishing point 3. We can do the same construction for this side. And if you are doing everything perfectly, if you are drawing there is another straight angle, another right angle, then we will take the same vanishing point 3. But of course there could be some margins of errors. So there could be 2 points, but it doesn't really matter because you are still drawing somewhere there. And if you found several vanishing points, which just by some mistake, by some error, it doesn't really matter. It would be a matter of fractions of degree. So right now we had found all vanishing points, and we can actually draw a box with this thing. So let's choose some color. For example, let's select red color, and we can draw there a box in a very simple way, like in all these fake tutorials about 3-point perspective. But now we are doing the correct box, which has right angles, which is not distorted, and for which we can actually control the viewing direction. But of course it is not a cube again. This method does not provide you with a cube. Drawing a cube will be discussed later, and it is more difficult. It will require the concept of measuring points, which would allow us to choose length in a consistent way. But before we know an idea of measuring point, it would be quite hard to draw a cube. So this is our box, which we are trying to draw at the very start.